Hello and welcome back, everybody. So today we're going to be talking about number theory. So number theory is a really nice thing to get started with because most of you are already familiar with a lot of the ideas that we're going to talk about. We're just going to talk about them on a little bit sort of a higher level, sort of a more rigorous level. And so basic number theory will be a great place to get started in your journey in doing proofs. So one of the things that we'll really want to focus on in this lecture is the idea of definitions. So we're going to be given some definitions of things that you're kind of already familiar with, things like even and odd integers and what it means for one integer to divide another integer, and a few others. But the idea here is we want to be focused more on the concept and the precise definition than we are with sort of, calculating things with numbers. And these will be important skills because in all of your sort of mathematical proofs that you're going to be doing, there's going to be definitions involved, and you have to follow them precisely, not only so that you get the right answer and you don't make mistakes, but also we have to have precise definitions that we all agree upon so that we can communicate to one another with a minimum of fuss. So with all that in mind, let's get started. And so first of all, before we get into too many definitions, just want to point out some notations for some common sets that we use a lot in math. So the first one there are the natural numbers. So these are just the whole numbers starting at 1 and moving upward, 1, 2, 3, 4, 5, 6, and so on. So the symbol there, it's a little bit hard to see, but it's a sort of fancy N that looks like that. After the natural numbers, we have a superset of that, the integers. So the integers include the natural numbers, but also 0 and all of the negative sort of whole numbers. So we call sort of positive, negative, and 0 whole numbers the integers. And we use this symbol to indicate the integers. Then we have the rational numbers, which is again a superset of the integers. So as you go down this list, each set that you find further down the list is a superset of the previous ones. So the rational numbers, these are all of the numbers that you can express as fractions of integers. So we usually indicate Q like that when we're doing it written by hand. Looks a little different than the print form of it, but it's just a Q with a line on the side of it like that. So things like 2/3 would be a rational number. But on the other hand, something like pi is not amongst the rational numbers because pi just simply cannot be expressed as a fraction, which is a non-trivial fact, but we're not going to prove it now. The next set of numbers, we don't really have a good definition for it right now. The definition of the real numbers is actually a bit technical. But so you can think of the real numbers as representing points on a number line. So somewhere on this number line is 0, and then there's 1, and there's 2, and so on. But there's also the points in between, like 1/2, so you get those rational numbers in there. But you also get those weird numbers like square root of 2 that can't be expressed as fractions. Even those kind of numbers have a point on the number line, right? So if you take the whole number line, that corresponds to the real numbers. And then the complex numbers are where you take a real number x plus I, and then you do a real number y. The x and the y here are real numbers, and I is the square root of -1, so the imaginary unit. We won't work with the complex numbers a whole lot in this class, but every once in a while it'll come up as an example. But you can take a whole course on properties of the real numbers and sort of functions on the real numbers, and we call this analysis. You've already had some analysis, we call it calculus. Analysis is sort of the theory, or real analysis is sort of like the theory of calculus. And that's one of the courses that you have to take in the math major. And then the complex numbers have a whole course devoted to them. It's called the complex analysis, which is an elective course you can take in our major. And then for the rest of this chapter, though, we're going to be focused on the integers. And so there are some axioms for the integers here. Now, axioms are just statements that you accept as fact. They're not proven. So axioms are taken as a hypothesis in the system that you're working in. It's not that you can't necessarily prove them, but if you can prove a fact in terms of more elementary facts, then it is no longer necessary as an axiom, something that you can just accept. If you can prove it, it doesn't have to be an axiom. So the things in this list really can't be proven as far as we know, but they're so simple we just kind of have to go, okay, that just seems to be a property. So for example, we're starting with a, b, and c are just any old integers. So anytime you add two integers together, you get an integer. Anytime you negate an integer, you get an integer is the second one. The third one here says if you multiply two integers, you get an integer. The fourth property, which is often called the commutative property of addition in the integers, just says that it doesn't make a difference what order you add two integers in. A plus b is b plus a. Similarly for multiplication in part 5. Part 6 is associativity of addition. It just says if you have three numbers to add together, it doesn't matter which two you choose to group together first to do adding, because adding has to be done two numbers at a time. So you can first add a times b, you can first add a plus b and then add c, or you can first add b and c together and then add a to that. That's associativity. 7 just says that 0 has a special property. When you add 0 to any other integer, you just get back that same integer. 8 is the additive identity property, that whenever you add a to negative a, you get 0. And then part 9 is a distributive property, that multiplication distributes over addition. So these are things that we just assume are true. And like I said, we wouldn't assume something as an axiom if we can prove it. So you may notice that these axioms don't include any facts about subtraction. One thing we need is a definition here. Let me squeeze it in here. A minus b is defined, equals, to be a plus negative b. And so we could prove fact 0.3 that for any integers a and b, a minus b is also an integer. So it's sort of the analog of property 4, the analog of property 1 in the list of axioms there, but for subtraction. But we don't need to assume it as an axiom because we can actually prove it. So here's how a proof of that would go. So let's let a and b be integers. Then we know that by property 2, negative b is an integer. So this is by 0.2 part 2. Next, a plus negative b is an integer. And this would be by axiom 0.2 part 1. Because we had already established that negative b is an integer. And we already knew that a was an integer, so if we add a and negative b, two integers together, we get back an integer. That's what part 1 says. That is, remember the definition of a minus b is a plus negative b. So we just showed that a minus b is an integer, and we're done. Here we're using the definition of a minus b as a plus negative b. So there you go. There's our first little proof. But the moral of the story here is that we didn't need to assume an axiom about subtraction because we can derive it from the previously established axioms. And that's how axiomatic systems always work. We're not going to be hugely focused on axiomatic systems, but it is sort of a deep subject in mathematics. There are long lists of axioms for just about every subject that you might want to study in math. There's axioms for real numbers, there's axioms for complex numbers, you name it, whatever subject you're working in, there's going to be some axioms. Things that we assume are true. Okay, so now let's get into some definitions that apply to integers. So the first three we'll look at are even, odd, and the term divides. To say an integer is even, our definition is going to be that it just means that you can factor a 2 out of it. So n is even if there exists some other integer r such that n is equal to 2 times r. I just think of that as n being even means I can factor a 2 out of it. After I factor the 2 out, what's left? Well, that's the r. Similarly, when we say m is odd, it just means it's an even number plus 1. So there would exist some integer s where m is equal to 2 times s, that's your even number, plus 1. Putting these definitions into practice here, why can we say 17 is odd? Well, according to our definition, It's because 17 is equal to 2 times an integer. Well, what integer is that? 8 plus 1. 17 is 2 times an integer plus 1. I want to point out here that 8 is an integer, so it complies with that definition. Similarly, I can say 24 is even because 24 is equal to 2 times 12, where 12 is an integer. It's important that this number that you're multiplying by 2 is an integer. It can't be some sort of fractional value. For example, it wouldn't do to say 17 is equal to 2 times 17 halves and then say that 17 is even because I expressed it as 2 times a number. Well, the number that 2 is multiplied by here is not an integer. So, I haven't just verified that 17 is even. So I want to point out that that number you're multiplying by is an integer. It doesn't work. More generally, when you're doing a proof, you may not be dealing with a very specific integer like 17 or 24. In the midst of your proof, it may be that you just have some integer q and it's even. So if I say q is an even integer here, what can I say about q? Well, I can say then there exists some integer. I don't have to use the very same letter that was in the definition. So for even integer, I had used r in that definition, but I could use k or whatever. I'm going to use k here. There exists some integer k such that q is equal to 2 times k. I know it looks like I haven't really done much, but being able to expand what the definition implies in the middle of a proof is something you do over and over in this class. So this sort of thing, what we just did, is really important. In the next example, we've got 2 integers in play, a and b, and I want to talk about, like how do we expand that into a more precise, or, in other words, how do we expand what we mean to say a and b are both odd integers? Well, we could do something like this. We could say, well, then there are integers. Got to give these new integers some names about p and q, such that, and then maybe a is equal to 2 times p plus 1, because it's odd, and b is 2 times q plus 1. Now notice, I didn't say, like, b is also 2 times p plus 1. We have to use a separate variable for b, because if I said b was 2p plus 1, and I also said a was 2p plus 1, that would say a and b are equal. But we don't know that a and b are equal here. We just know that a and b are both odd. The commonality that they have is being odd, not being exactly equal to one another. So we have to use 2 separate, variables p and q there to capture that. In definition 0.5 at the bottom here, a and b are integers, and we're assuming a is not equal to 0 because we're going to be dividing by a. So we say a divides b, and we have this notation a bar b to indicate that relationship. So when we say a divides b here, we're talking about a relationship between 2 integers. We're not talking about the result of dividing a by b, which would be some number. We're just talking about a relationship. It's kind of like less than or greater than. It's a relationship between 2 numbers. Anyway, what does that mean? It means that there exists an integer n such that b is equal to a times n. So in other words, whenever we say a divides b, it means that we can factor a out of b. And for that reason, we use this terminology a is a factor of b to mean the same thing. Or we say b is a multiple of a. So we multiply a by something to get b, which is captured in this equation right here. Down here at the bottom, I have a couple of examples to just illustrate the concept. Why can we say 3 divides 18? Well, we can say that because 18 is equal to 3 times an integer. What integer is that? Well, of course, that would be 6. And then similarly, we can say 5 divides negative 45. Don't be put off that there's a negative number there. The definition allows for negative numbers. The only thing we can't do is have the thing we're dividing by be 0. But we can't have negative numbers. So 5 divides negative 45 because I can write negative 45 is equal to 5 times negative 9. And we know negative 9 is an integer. I want to give you a little bit of a warning on notation. So when we do a bar b, it's not the same as like a divided by b or b divided by a. So a divides b with the vertical bar indicates a relationship between 2 numbers. But when you write a divided by b or b divided by a, that's a number. That's a fraction, right? Don't get those notations confused. They're related to one another, but they're not the same. And the way that I keep them separated in my mind is that I understand that this notation indicates a relationship, whereas this notation here and here indicates a number, the number that results from dividing A into B or B into A. And just like we did with even and odd, we may have more general situations. Like, for example, if I say, hey, suppose 5 divides t, what does that mean? What can I say? Well, one thing I could write would be to say, then there exists an integer, and I have the freedom to call it whatever I want. Maybe I'll call it s this time, such that t is equal to 5 times s. So in other words, to say 5 divides t means I can factor 5 out of t. And then we use the language that 5 is a factor of t. We also say t is a multiple of 5. So again, this looks like I'm not doing much, but expanding out what the definition actually means is really important. It's an important skill that you use a lot in this class. And remembering that words have definitions, and we use those precise definitions in the midst of our proofs, really contributes to successful proof writing. If you just try to make it up or just say what you kind of think something means, it doesn't quite cut it. You've really got to use the precise definition. Okay, another concept that you're probably familiar with are the concepts of prime and composite integers. A prime number is an integer that's greater than or equal to 2. So we don't consider the idea of prime numbers for negative integers or even 0 or 1. We got to start with something bigger than or equal to 2. But we'd say an integer greater than or equal to 2 is prime if the only factors, or the only numbers that divide it, are the number n and the number 1. And then if a number is not prime, we say it's composite. So composite is just whatever's left over after you take whatever's left out of the integers greater than or equal to 2 after you take out the primes. Whatever's left is composite. But really what it means is that a number's composite means that it has some other factors besides 1 and itself. One thing to point out here, a couple notes. 1 is neither prime nor composite. So 1 just isn't considered part of the definition. Okay, the definition only starts with n's greater than or equal to 2. And similarly, negative numbers or 0, you can't consider them as being prime or composite. They're just not part of the definition. So the first several primes are, if I just start thinking about, okay, starting at 2, what numbers have only divisors of that number and itself? Well, you've got 2 has divisors 2 and 1. 3 has divisors 3 and 1 only. 4 has divisors 1, 2, and 4, so it's not prime. 5 is prime. 6 is not because it's got divisors 1, 2, 3, and 6. And so on. So, you get 7, and then 8, no, 9, no, 10, no, 11, yes, 13, 14, 15, no, 16, 17. Okay, 17 would be your next one, then 19, and so on. It turns out, as we'll prove a little later, that there are infinitely many primes. They do get further and further apart on the average as you move further out into the integers. Like initially you got lots of primes, right? But eventually they kind of get more spread out, and you might start to wonder, well, maybe you run out of them after a while. But it turns out there are infinitely many primes. 6 is composite because 6 does have other divisors, right? 6 has divisors 1, 2, 3, and 6. In particular, 2 and 3 here are factors not equal to 1 or 6. So that's what makes this number composite. You may have heard of the fundamental theorem of arithmetic. It says that every integer greater than 1 can be factored uniquely as the product of prime numbers. So for example, 242 there at the bottom. How does that factor? Well, you may remember doing something like this when you were a kid. 242, you make a factor tree for it. I see that that's even, so I could do 2 into it. How many times does 2 go in there? 121 times. Oh, and then I recognize 121 is 11 times 11. And so I see that the prime factors of 242 are 2, 11, and 11. So 242 can be factored as 2 times 11 times 11, or if you want, 2 times 11 squared. The order in which you write the prime numbers doesn't matter. So the uniqueness is just the actual primes that are in the list of primes that divide the thing. And sometimes you get repeated primes like 11 squared here. Okay, so now what I want you to do is to take some few minutes and do this skills check on the definitions of even, odd, and divides. So take a few minutes and work these problems out on your own, and then when you come back to the video, we'll work through them together. All right, welcome back. So for part A, why is negative 42 even? Well, it's because we can factor a 2 out of negative 42 and express negative 42 as 2 times negative 21. And we'll note that negative 21 is an integer. Whatever number is multiplied by 2 has to be an integer, right? On part B, the reason 173 is odd is because we can express it as an even number plus 1. So it's because 173 can be written as 2 times what? Well, let's see. 86. 2 times 86 would give you 172 and plus 1. And we'll point out that 86 is an integer as required by the definition. Okay, part C. Why does 8 divide 96? You know, if we go, maybe we can cheat a little bit and go, okay, 96. How many times does 8 go into that? Let's see. Well, it's just 1, 8, 16, 2. I guess I should know my 12 multiplication table also. The reason that 8 divides 96 is because we can write 96 as 8 times 12. And 12 is an integer as required by the definition of divides. So saying 8 divides 96 is the same as, you can factor 8 out of 96. Okay, is 41 prime or composite? 41 is in fact prime, and the reason is that 41's only divisors are 1 and 41. Now you can verify this by just checking each integer between 1 and 41 to make sure that none of them divide into 41. That's a really crude way of doing it. In fact, though, you don't ever have to check up to more than half of the number, because no number that's larger than half of a number can divide it. But that's pretty easily verifiable there. Okay, on part 2, I'm using Greek letters here. Suppose alpha, beta, and gamma are integers, and we know gamma is not equal to 0. And let's further suppose that we know that beta can be expressed as gamma times alpha. So the question, part A of number 2, is what can we say about the relationship between gamma and alpha? In fact, we can't say anything about the relationship between gamma and alpha. In order for there to be a relationship in terms of the definitions under discussion here, in particular divides, we would need alpha and gamma to be on opposite sides of that equation. But between gamma and beta, we can see that, we've taken beta and factored a gamma out of it. So that must mean that gamma divides beta, right? So again, repeating, we've taken beta and factored gamma out of it to get beta equals gamma times alpha. And we know that also gamma is not 0. So that equation satisfies the definition of gamma divides beta, or gamma is a factor of beta, or beta is a multiple of gamma, however you want to say it. Now, a concept that is closely related to the concept of divides comes in the form of the division algorithm. So the division algorithm is actually a theorem that can be proven, although we don't have the tools that we would need to prove it right now. It requires a process called mathematical induction. But here's what the division algorithm says. It's kind of a complicated statement, but basically the division algorithm is just saying, you remember that process of doing long division when you were a kid? It always works, is what it says. Whenever you do long division, you're always going to get a unique quotient and a unique remainder. Doesn't matter how you do the division. If you do the division process right, you're going to get the unique answer every time. The setup here is that we have a and b are integers, and this time b, we're going to insist that b is greater than 0. B is the number that we're going to divide by here. We call it the divisor. Then there exist unique integers q and r. Q is going to be called the quotient, and r is going to be called the remainder, where b, or rather a, can be written as b times the quotient plus the remainder. And we know that the remainder is greater than or equal to 0, but less than the number you're dividing by, b. For example, just picking a few easy numbers here. What if you do 48 divided by 9? When you do 48 divided by 9, 9 is your B, the number you're dividing by, and 48 is your A, right? And so you do long division, you go 9 into 48. Now let's see, that would go, what, 5 times? And then 9 times 5 is 45, subtract there, and you get 3. So you get a remainder of 3. So your Q is equal to 5, and your R is equal to 3. And in fact, the number that you're dividing into, the dividend, 48, can be written as 9 times the quotient, which is 5, plus the remainder 3. So 5 here is your quotient, R here is your remainder. And notice that the remainder here satisfies the inequality that it's supposed to satisfy. The remainder is between 0 and 9, strictly less than 9. So the division algorithm guarantees that you can always do this. Now, what if you want to divide into a negative number? In the division algorithm, the number that you're dividing by has to be positive, but the number that you're dividing into does not have to be positive. What if you divide 9 into negative 48? Well, let's see how that would go. If you divide 9 into negative 48, first I'm going to show you the wrong way to do it. So you might think, well, since that's a negative number there, I'll do like, well, negative 9 times, I'll put a negative 5 at the top. And then, like, what happens when you subtract here? So remember, you got to subtract, and you'd have like a negative 3 left over at the end. Well, notice that what you're trying to get for a remainder here is not positive, and the remainder has to be positive, so this is not going to work. Instead, what you have to do is overshoot a little bit. Do it like this, 9 times, so 9 goes into negative 48. You need to overshoot by 1 when you're dividing into a negative number, so it would go negative 6 times, and then you'd have negative 54 here, and now when you subtract that, you actually end up with a positive remainder of 6. So now your Q is equal to negative 6, and your remainder is equal to positive 6, and you see from this that the dividend, negative 48, is equal to the divisor 9 times negative 6 plus the remainder 6. Negative 6 here is your Q, and this is your R. And notice now that your remainder satisfies the inequality that it's supposed to satisfy. It's between 0 and 9, but strictly less than 9. So we can divide into negative numbers. You just have to think to overshoot a little bit. And now here's a nice theorem that tells us, hey, what the division algorithm does coincides with what our definition of divides is. So there are two things going on, right? We had a definition of divides, which expressed a relationship between two numbers, and we had a division algorithm, which basically tells us that we can do long division and get a quotient and a remainder. So there's definitely a connection between divides and division, unsurprisingly, and it's captured here in Theorem 0.12. So the setup is that we have two integers, and we're going to suppose that the number a is greater than 0 because that's the number that we're going to be dividing by. And we're going to let r be the remainder upon division of b by a. So the theorem says a divides b if and only if r equals 0. So even though we haven't talked about how to do proof methods a lot here, I wanted to give you a quick little proof of this. The if and only if part means that these two facts imply each other separately. So a divides b implies that the remainder must be 0 when you divide b by a using the division algorithm. But also, if you do division and you get a remainder of 0, then that tells you that a divides b. So let me give you how that proof goes. So going sort of in the forward direction, let's start off the proof by saying, well, let's let a and b be integers with a greater than 0, and suppose r is the remainder upon doing b divided by a per the division algorithm. And so then going in the forward direction, I'd suppose a divides b. Well, what does that mean? Well, by definition of divides, there exists an integer, let's say k, such that b is equal to a times k. But this is equal to a times k plus 0. And then by the division algorithm, in particular the uniqueness component of it, by the uniqueness q and r in the division algorithm, we have quotient q equals k and remainder r equals 0. which satisfies the required inequality from the division algorithm. So in particular, we know r is equal to 0, which is what we wanted to prove. We wanted to prove that r is equal to 0 if we know a divides b. And we get that from the uniqueness given in the division algorithm, because there's only one quotient and only one remainder that satisfy this equation, a equals bq plus r. All right, so going the other way, suppose that remainder is equal to 0. Then the division algorithm says there exists some q in the integers such that, okay, we're dividing by a, so it'd be b equals a times q, and then we just said suppose that the remainder was 0. Well, that is b is equal to a times q, where q is an integer. And then you see that this bit right here is exactly the definition of a divides b. So, end of proof. But I think this theorem is not telling you anything particularly mind-blowing. When we say a divides b, one way we often say is that a divides b evenly, right? Like it goes into it with a remainder of 0. So when you say a divides b, we're talking about that sense of a divides b evenly, which means r equals 0. All right, now's the time to do a little skills check on the division algorithm to make sure that you understand how to do it and how to find the quotient and remainder and how to write the associated equation that goes with the division algorithm. So we've got 3 questions here that I'd like you to quickly work on your own, pausing the video, and when you're finished, come back and we'll work through it together. All right, welcome back. So let's take a few minutes to run through these problems. Make sure you did them correctly. Set up a little room to do some scratch work over here. So for the first one, we need to divide 417 by 15 and find the quotient and remainder. So let me just do long division over here on the side. 15 goes. So it looks like q is equal to 27. R is equal to 12, and the associated equation is that 417 is equal to 27 times our divisor, which was 15, plus the remainder, which was 12. We could check that, we got our answer right by checking that that last equation is actually true. So if I do 27 times 15, what do I get here? Let's see, 30. 4, 5, and then if we add 12 to that, we get 417. So it checks out. And then for the second problem, we need to divide negative 87 by 13 to find the quotient and remainder, and then write down the associated equation. So let me erase this previous scratch work and do the next one. So this one, you just have to be careful. You're dividing into a negative number, so we're going 13 into negative 87, so we have to remember to sort of overshoot a little bit so that we get a positive remainder. So let's see. So if you had done your long division like this, which would be incorrect, if you had gone negative 6 and then had there negative 78, when you would subtract here, you would be left with a negative remainder, right? You would be left with negative 9. And you can't have a remainder be negative. The remainder has to be greater than or equal to 0 and less than the number you're dividing by. So this won't work. All right, so writing down the answer, our quotient was negative 7. Our remainder is 4. And this can be checked by writing down the equation. Negative 87 is equal to our divisor, which was 13, times our quotient, negative 7, plus our remainder. And that checks out. And then for number 3 here, we're given this equation and asked what can we infer from it? Well, if you're thinking in terms of this context of the division algorithm, you can infer a couple of different things actually. You can infer that upon division of 78 by 8, the quotient is 9 and remainder is 6. But you can also say that upon division of 78 by 9, the quotient is 8 and the remainder is 6. The division algorithm tells you that numbers satisfying that equation are unique in that sense. So I know that if I divide by 8, I've got to get the quotient's got to be 9. There's only one integer that satisfies that equation in that spot where the 9 is, and giving that remainder of 6. And similarly, if you divide by 9, there's only one quotient and remainder upon that division, and that equation captures it. So there you go. A little notational point right here is that when we use that vertical bar with a little slash through it, that's how we express A does not divide B. And Theorem 0.13 here gives you a way to think about what does A not divide B mean, really. How can we sort of break that out into something a little bit more useful? So same setup as before. We have the integers A and B. The number we're dividing by is greater than 0, and R is the remainder. That's the setup. So A does not divide B if and only if the remainder is not 0. Well, if you think about it, and with a little bit of logic that we'll learn a little bit later, we can see that Theorem 0.13 is just an equivalent formulation of the previous theorem we just talked about, 0.12. So I'm not going to bother proving it because it's really just an equivalent statement of the previous thing. But it gives us a nice way to think about does not divide. So just a real quick, with some very specific numbers example here. Why do we know 6 does not divide 20? Well, because we can divide 6 into 20 and see the remainder is not 0, right? Because something like this, upon division of 20 by 6, we get a remainder of 2, right? Which is not equal to 0. Now, how about in a little bit more general of a setting? Suppose n is just some integer, and we know 3 does not divide n. Then what can we say about the remainder upon dividing n by 3? What are the possibilities for the remainder? So essentially I'm saying, what if you do this? You go 3 into n, you get some quotient. What is the remainder got to be if we know 3 does not divide n? Well, the remainder can't be 0, right? Because if the remainder were 0, then that would mean that 3 does divide n. So we know r can't be 0. So what can r be then? Well, we also know from the division algorithm that the remainder can't be as large or larger than the number you're dividing by. So we know that r has to be less than 3, right? So that only leaves two possibilities. R can be equal to 1, or r can be equal to 2. R can't be 0, because that would mean that 3 does divide n, and r can't be 3 or more, because the division algorithm prohibits the remainder from being 3 or larger. So that's all. So whenever you know one number does not divide into another number evenly, there's a finite number of possibilities for what the remainder can be, which a fact that we'll use a little bit later when we're doing some proofs. All right, next concept to talk about, and this may be a new one for you. You may or may not have seen it, but it's called modular congruence of integers. So it's sort of a way that we kind of think about two integers as being kind of the same, but it's another relationship we can express between two integers. So in this setup, we have the a and b are integers, and then we have a third integer n, which you're going to assume is greater than or equal to 2. And then we have this relationship where we'd say a is congruent to b modulo n, and we have some notation for it. I kind of prefer this notation right here, a triple bar subscript n b. So that would read a is congruent to b mod n. All it means is that n divides the difference between a and b. So if you take the two numbers a and b, you subtract one from the other, if n divides that evenly, then that's what it means to say a is congruent to b. That's a strange relationship. It possibly doesn't really have any intuitive sense. we'll get to like why it makes some sense in a little bit, but let me just let's just check that we can work with the definition with some really concrete numbers here. So the first example I have here is I'm claiming that 2 is congruent modulo 5 to 17. 2 can be your A from the definition, and 17 can be your B, and 5 is going to be your N. So we need to check that N divides A minus B. So what is A minus B? Well, that's 2 minus 17, which is negative 15. And I know that 5 divides negative 15 because I can write negative 15 as 5 times negative 3 and point out that negative 3 is an integer here. So 5 divides 2 minus 17. So the upshot here, the reason this is true, 2 is congruent modulo 5 to 17, is because we can argue this is true. 5 divides 2 minus 17. Similarly, we can say negative 4 is congruent to 26 modulo 10, because if I take the difference between those two numbers, so if I do negative 4 minus 26, that would be negative 30, which is 10 times negative 3, and negative 3 again is an integer. So I can see that 10 divides negative 4 minus 26. Again, the reason this is true is because this is true. And by the way, in this definition, the number n is sort of what you're dividing by in all these problems. It's called the modulus. Here I want to give you sort of a way to think about modular congruence. Let's start off with this picture on the far left here, and I'm thinking about a modulus of 5. So our n is equal to 5 here, okay? So I want to think about numbers that are congruent to 0 modulo 5. Well, those would just be the multiples of 5. So think about a clock that only has 5 hours, like in this picture on the left here. So you can go 0, 1, 2, 3, 4 around it, and then just keep counting, like 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. So all of these numbers are going to be congruent to each other modulo 5. And all these numbers, 1, 6, and 11, are going to be congruent to each other modulo 5. And all of these numbers are going to be congruent to each other modulo 5. So if you take any of the numbers in the same position on the clock and you subtract them, you're going to get a multiple of 5. For example, 2 minus 12 is negative 10. That's a multiple of 5. Or over here, if you do 13 minus 8, that's a multiple of 5. Over here, if you do 14 minus 4, that's a multiple of 5. So, and if you think about this in terms of a 12-hour clock, in the second picture, I could do something like, you count around the clock one time, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then keep going around, 12, 13, 14, 15, 16, 17, 18, 19, 20, so on. Then you get to 24, 25, 26. If you went around again, you'd get to like 36, 37, 38. And any of the numbers that are labeling a specific spot on the clock are congruent modulo 12. So the numbers that I have circled right now are all congruent to each other modulo 12, because if you take any two of them and subtract, the difference is a multiple of 12. For example, 38 minus 14, the difference is 24. That's a multiple of 12. Another way that you can see mod 5 is on a number line. So take a number line and put the multiples of 5 on the number line. And then you got the in-between integers. So like, for example, 2 here. So if you pick all the numbers that are in the same relative position between the multiples of 5, those numbers are going to be congruent modulo 5. So 7, 12, over here, negative 3. All these numbers in green are congruent modulo 12. Notice that they're all 5 apart from one another, right? Or multiples of 5 apart from one another. So this is the difference of 5 here, 5 here, 5 here, so on. So anyway, there's a few ways to visualize what congruence mod n is kind of looking like. Okay, this would be a good place to stop for a second and do a skills check. This will be a pretty quick one. Take a few minutes and work on these, pause the video, and when you come back, we'll work on these together. All right, welcome back. Okay, first question, true or false? Explain whether these stated congruences hold up. Well, on part A, on both of them, what you need to do is subtract the two numbers from one another and then determine if the modulus divides that difference. So on part A here, if I do 67 minus 22, I get 45. And we see that 15, the modulus in this problem, that's the subscript on the congruence symbol. And we see that 15 does divide 45. So true, the statement is true. On the second one, well, honestly, I can kind of tell right away that it's false. When you're doing congruence modulo 2, you're just talking about even and odd, basically. Everything that's congruent to 0 is even, and everything that's congruent to 1 is odd. But if you just follow the definition, I could take 18,720 and subtract 1271. It doesn't really make a difference which way you subtract. Maybe I'll subtract them vertically just to make it a little easier. 2 does not divide 17,449 because, well, that's an odd number, and 2 doesn't divide an odd number. So this is false. Those two numbers were not congruent modulo 2. Okay, for number 2, well, one number that I know is congruent to 7 modulo 10 is 7 itself, because if you do 7 minus 7, you get 0, and you can divide 10 into 0 with a quotient of 0 and a remainder of 0. So 7 itself is congruent to 7 modulo 10, so I'll mark that one. And basically all the other numbers that are congruent to 7 are numbers that are a difference of a multiple of 10 from 7. So numbers like 17, the difference between 7 and 17 is 10, or negative 2 here, I'm sorry, negative 3, or negative 13. The spacing between these numbers is 10. And so if you take any two of them, the difference would be 10, or the difference would be a multiple of 10. If you wanted to keep going out here, is negative 23 is probably just enough room there for that one. Way out here somewhere, maybe it's just right about there, 27 would be one of them, and so on. All right. Okay, here we have in Theorem 0.17 a really cool fact, and a pretty important one. It just says that if you have some number a, and you're going to divide it by n, where n is greater than or equal to 2, then a will actually be congruent to whatever the remainder is when you divide by n. So you always have a way to take a number, it might be a number that's much larger than n, some gigantic number, and you can always find a number that's congruent to it that's relatively small compared to n. In fact, it's the remainder. The remainder is always between 0 and n, right? Less than n. So this gives you a way to sort of pare down a large number and find something that's congruent to it, modulo n, that's much smaller. So by way of example, let me jump down to the example here real quick before we do I want to prove this theorem for you, just to start getting the idea into our mind that we can prove theorems and we can use our definitions to do so. And yeah, we're going to talk about proof methods in the near future and get better at that, but it's still, I think, good to go ahead and start doing that. But before I want to prove this theorem, I want to give you an example of the sort of thing that I'm talking about, why this theorem is useful. So I've got this big number here, a equals 18,472, and I've got a modulus of n equals 12. And the idea is I want to find a number that's congruent to this big number a, modulo 12, that's much smaller. And so all I need to do then is to find the remainder when I divide 12 into that A equals 18,472. So let me go over here to the side and do that long division. So that's our remainder there, 4. So what this previous theorem tells us is something quite nice, I think. So from long division, we just found out that 18,472 is congruent mod 12 to 4. So if I were thinking about this as a position on a clock, the number 18,472 is in the 4 o'clock position. Let's go ahead and do the proof for theorem 0.17. Okay, so what we need to establish is if we know r is the remainder when we divide our maybe big number a by n, we want to show that that remainder is congruent to a. So what we have to do is show that if I take a and subtract the remainder, I get something that's a multiple of n. But lucky for us, we have the division algorithm which is going to provide this to us pretty easily. So check it out. So we'll let r be that remainder as specified in the statement. Now, the division algorithm says, I'm going to abbreviate that DA. The division algorithm provides the existence of Q in the integers such that we're dividing into A, so A would be equal to, and we're dividing by n, and then times the quotient, and then plus the remainder. And we happen to know that that remainder satisfies this inequality here. Now from this equation here, A equals n times Q plus R, we can subtract R from both sides to get A minus R is equal to n times Q. So notice that the difference between A and R is a multiple of n. And so what we have is, by definition of divides, we have that n divides A minus R, because A minus R is a multiple of n according to the equation. But then this is exactly the definition of what it means for A and R to be congruent modulo n. So we have the result we want. A is congruent modulo n to that remainder R. All right, very cool. And then the next topic that we'll want to talk about are common residues. So what are common residues? Well, simply put, common residues are just remainders. So if in this definition here we have a and n are integers, and n is our modulus that's greater than or equal to 2, and r is going to be that remainder whenever we divide a by n, then we're just going to give the remainder a new name. We're going to call it the common residue of a modulo n, and we're going to have some new notation. We're going to call the remainder when you divide a by n, we're going to call it a mod n, like that. Or sometimes we call it a percent n. This is really common in computer science, like in computer programming languages. This is usually just built in as something that the compiler can calculate. If you do a percent n, it just gives you the remainder when you divide a by n. So real quick, a couple of examples. 47 mod 7, that just means divide 7 into 47 and report the remainder. Well, 7 into 47, let's see, looks like we get a remainder of 5 there, right? Because 7 goes into 47 6 times, you get 42, and then a remainder of 5. And 3%, or negative 25% 3, that just means divide 3 into negative 25 and report the remainder. Well, this is going to be 2. If you think about it, 3 into negative 25, we've got to do the overshooting thing. So we would do times negative 9 here, negative 27, and when you subtract, the remainder would be 2, like that. Residues are kind of nice. It's just a quick way to figure out relative positions of things in a list. So what we just did, the remainder just, like imagine you've got like in that first one where we were going mod 7, imagine you have a clock with 7 hours on it. And then if someone said, okay, what position would 47 o'clock be in? Well, 47 o'clock would be in the 5 position on that clock. And if we had a 3-hour clock and someone asked, what position is negative 25 on that 3-hour clock? Well, it would be in the 2 o'clock position. I think of this a lot when I'm doing computer programming and I have lists. Maybe I have a list of length 100, but for some reason I do some arithmetic and I need to access, like, what's the 143rd entry in that list? Well, if the list is only 100 long, I can't really pick out the 143rd position, but I can go mod 100 and just have 43. So that's the sort of thing that you can do with residues. It sort of just gives you relative positions in lists. The last little topic that we'll talk about here whenever we're doing properties of integers is the idea of addition and multiplication modulo n. So this relies on the concept of residues. So we have two concepts, an addition and a multiplication. But the definition is pretty simple. So we got a new kind of addition, plus with a subscript of n. So this is modular addition. And then down here we have a multiplication with a subscript of n. That's modular multiplication. So the way it works is if I want to add two numbers modulo n, I just add them together in the usual way, but then take the remainder when I divide by n. In other words, take the residue. It turns out that you can actually do the residues first and then add if it's helpful. But like right here on this first example, to do 9 plus 8 modulo 10, all I got to do is just add those two numbers together. So that'd be 9 plus 8. And then take the residue modulo 10, right? So that would be 17 modulo 10. Or in other words, 7 would be your final answer. And if I wanted to multiply those two numbers, well, first I would just multiply them. So I'd do 9 times 8. And then I'll take the residue modulo 10. So if I multiply 9 times 8, what do I get? I think that would be 72. I'm going to take the residue modulo 10. And that would be 2, would be the remainder when you divide 10 into 72. If you wanted to do some really big, like some bigger numbers, you could save yourself some trouble. Like here's another example. What if I wanted to do like 19 times modulo 10, I don't know, 183. Maybe I'm going to think, oh man, it's a really big drag to have to go over here and do 183 times 19, and I don't want to have to do that multiplication. Actually, it turns out you can take the residues first before you multiply. Turns out you can just do 9 is the first residue, and then you're doing multiplication modulo 10, and then the residue for 183 is 3, so that'd be 27 modulo 10, which is the same as 7. So that's a lot easier to, if you first take the residues here and here before you multiply. That didn't really help us on the first two examples, but when the number's starting getting big, it's helpful. All right, so that's all I've got for you today on properties of integers. Again, I want to emphasize what was important here. The calculations and actually doing long division, I'm going to assume you already knew how to do long division since like 2nd or 3rd grade. Maybe you don't do it a lot and you get a little rusty on it, but you basically know how to do long division, right? That's not really the point. The point is we want to have some definitions and some theorems about integers that we can work with in order to start our journey into doing proofs. And so what I really want you to take away from today's lecture is that these things, these concepts like even, odd, divides, division algorithm, congruence, modulo n, that sort of thing, all has a very firm definition, and you can convert that definition into a more meaningful statement in the midst of your proof, okay? So being able to work it with very specific numbers is important, but you need to be able to make the leap to speaking in more general terms about, hey, what if 3 does not divide some integer t? What does that mean? So anyway, that's the takeaway from today. And then next we'll start our journey into proofs by talking a bit about logic. Okay, here's one last skills check. This one will cover residues and modular arithmetic. So pause your video and work on these 4 problems. This shouldn't take very long. It's just amounts to doing some division and figuring out what remainders are, basically. Maybe doing a little addition or multiplication while you're at it. So take a few minutes, do these, and come back and we'll work them together. All right, welcome back. So let's see what we get for the first one. 45 mod 3. So if I divide 3 into 45, I actually get a remainder of 0 because 3 times 15 is 45. So this one will just be 0. Negative 71 mod 5, what's the residue there? Well, if I divide 5 into 71, I'm going to get a remainder of 4 actually. So this will be 4. Remember, this is one of those ones where if you're dividing into a negative number, you have to overshoot a little bit by 1. So your calculation would look like that, and you'd get a remainder of 4. On number 3, so remember the trick I told you about, you can actually go ahead and compute the residues before you do the addition if you like to get smaller numbers. So the residue of 85 modulo 4 would be 1, and the residue of 53 modulo 4 would also be 1, and so this works out to be 2. All right, for number 4, we can also use the trick where we calculate the residues before we multiply. So one thing you may notice for 1017, if you add up the digits, you get 9. And that's a trick I learned when I was a kid, that if you just add the digits of numbers, you can tell if it's divisible by 3. If the sum of the digits is divisible by 3, then the number itself is divisible by 3. So since that first number is divisible by 3, 1017, its residue is 0 modulo 3. And if I divide 3 into 841, I'm going to see that the remainder is 1. So you get 0 times 1 modulo 3, but then I just do that product and I get 0. I get 0 modulo 3. All right, that's it for this lesson. Next lesson is going to center on logic, and then we will get into doing proofwriting very soon after that. So stay tuned for that, and I'll see you again soon. Bye now.